This slide is a summary version of the previous one, so your narration can reinforce the main teaching point. Core data are multidisciplinary. Core helps geology, petrophysics, reservoir engineering, and logging interpretation all at once. I would tell you that in real field studies, the most valuable reservoirs are often the ones where core data are used effectively across departments. Geologists use it to interpret depositional environments. Petrophysicists use it to calibrate saturation and porosity models. Reservoir engineers use it to estimate flow behavior. Geomechanics teams use it to evaluate stiffness and brittleness. So core is a shared asset across the petroleum workflow. This slide focuses on slabbed core, photographs, sedimentology, lithology, and stratigraphy. When a whole core is cut longitudinally and described visually, geologists can identify bedding, lamination, grain size variation, sedimentary structures, fractures, stylolites, cemented intervals, and other features. This is important because not all reservoir information comes from equations. Many crucial insights come from simply observing the rock directly. You may see layering that explains permeability barriers, coarser beds that form flow units, or fracture systems that strongly affect production. So slabbed core description is one of the most intuitive and geologically rich components of core analysis. This slide continues the slabbed core discussion, but now the emphasis is on lithology and structure. The visual core allows us to interpret how the rock was deposited, whether it is layered or massive, how fractures or stylolites are distributed, and whether there are abrupt changes in facies. This matters because structure and heterogeneity strongly influence reservoir behavior. A thin shale lamina, for example, may act as a local barrier to vertical flow. A more fractured interval may provide enhanced permeability. So even before laboratory testing, visual core description already gives us an early model of reservoir architecture. Now we move to thin sections, which allow microscopic examination of the rock. Thin sections help identify pore size distribution, packing, grain size, sorting, porosity, mineral abundance, fabric, rock classification, diagenesis, and porosity origin. This is a big step in scale. Instead of observing the core by eye, we now observe the rock under the microscope. Thin section analysis helps answer deeper questions such as, is the porosity primary or secondary? Is permeability controlled by grain packing, dissolution, fractures, or cementation? Is the reservoir quality depositional in origin, or has it been modified by diagenesis? This is why thin section petrography is so valuable in reservoir characterization. This slide emphasizes grain size. The deck notes that porosity may be relatively independent of grain size, but permeability tends to increase with larger grain size. That is because larger grains often create larger pore throats and therefore less resistance to fluid flow. This is a very helpful conceptual distinction for students. Two rocks can have similar porosity but very different permeability if one has much finer grains. So again, storage and flow are not the same thing. Grain size is one of the reasons why rocks with comparable porosity may produce very differently. This slide focuses on sorting, which means the uniformity of grain size. Better sorted sediments tend to preserve more effective pore systems because similarly sized grains pack in a way that leaves more connected pore pathways. Pore sorting means smaller grains can fill the spaces between larger grains, reducing connectivity. So here, I would tell students that sorting is one of the most geologically intuitive predictors of reservoir quality. Good sorting usually supports better permeability, while poor sorting often reduces it. This is why sedimentological interpretation is directly tied to petrophysical performance. This slide repeats the thin section themes and is a good place to summarize. Thin sections help us understand pore geometry, diagenesis, porosity type, and environmental evidence. This means that they tell us not only what the rock looks like now, but also how it became that way. You can emphasize that thin sections are especially important in complex reservoirs such as carbonates, where pore systems may be highly heterogeneous and strongly altered by diagenesis.